Welcome everyone. Hi. This is I've called this talk "Monsters in the Dark: Hunting for the Most Extreme Galaxies in the Universe." This is a subject that's very near and dear to my heart because on the rare occasion that I get to do some science, this is my area of research. So I think I find it very, very fascinating. I've called this talk "Searching for the Universe's Most Massive Galaxies," and I think I'm just going to kind of set the scene. I'm assuming for this group, I don't want to belabor the point too much. But for anyone that's not familiar, this is a galaxy. Galaxies are these big clouds of gas and dust and stars. They are these vast agglomerations of matter. This is an artist's impression of a very famous galaxy, the Milky Way, which is the galaxy we live in. Our Milky Way is a pretty impressive galaxy as all these things go. It's on the large side of things. Galaxies are anywhere from a few million stars, maybe on the low end, up to maybe 1 trillion stars on the high end. Our galaxy is a large-ish galaxy, somewhere between 200 billion and 400 billion stars in our Milky Way. For anyone familiar with Monty Python's Meaning of Life, they have a galaxy song where they tell you all about the Milky Way and get all their numbers exactly spot on, which is very nice. They describe the Milky Way as being 100,000 light years side to side. And we are about 2/3 of the way out in one of these little spurs here. For the longest time, we thought that the Milky Way was the only galaxy in the universe. Obviously, Edwin Hubble around 100 years ago came along and disabused us of that notion. And since the early 1920s, we've been living in a universe where the Milky Way that you see on the screen here is just one very kind of tiny speck. And we live in the middle of a whole zoo of different galaxies of all kind of shapes and sizes and colors. We can look at some galaxies nearby us. This is Andromeda. For example, M31, a very popular observing object. This is M31 as seen in the ultraviolet with the Galaxy satellite, actually. So you can see all the very, very young, hot blue stars highlighted here in the UV. Andromeda is a pretty similar galaxy to our Milky Way. They're both what we call these grand design spirals. For the longest time, we thought Andromeda was a bit bigger than our Milky Way. Now, the mass of Andromeda has been revised downwards a bit, and the mass of the Milky Way has been revised upwards a little bit. So now we think that Andromeda and the Milky Way are more kind of like cosmic twins than we previously thought. So the Andromeda galaxy is about 2.5 million light years away. It's our nearest neighbor big galaxy. We can kind of zoom out yet again and have a look at our little slice of the universe. So this is the local group of galaxies, and you can think of it as our little cosmic backyard. So here you have the Milky Way, and here you have Andromeda. This is kind of finding that Milky Way and Andromeda are kind of comparable in size. So you can see they've drawn Andromeda as being a bit bigger. And the interesting thing is that beyond the grand spirals, beyond the Milky Way and Andromeda, you can see like the little fluffy triangulum galaxy. This is what's called a flocculent spiral galaxy. Then also these little dwarf galaxies, including the small and large Magellanic Clouds, so these dwarf galaxy satellites of our Milky Way. The point I really want to highlight is that there is an absolute zoo of galaxy types. I think if you ask a member of the general public to imagine a galaxy, they'll typically think of a grand design spiral, not dissimilar to the Milky Way. But there are all kinds of things that we call galaxies. There are little irregular galaxies like the Magellanic Clouds. There are fluffy spirals. There are regular spirals. There's a whole array of galaxy types. There is one galaxy type, however, that we don't have in our local group. And that's just because they're very rare. Like the average spatial density of this galaxy type is low enough that in any given kind of cosmic backyard like this one, you're unlikely to have one. And those are the giant elliptical galaxies. They're not quite as visually impressive as many of the other types. Spiral galaxies are a favorite target of stargazers for a reason, right? These elliptical galaxies tend to look like fairly boring, blobby egg-shaped things. This one is M87. It's a very, very massive galaxy, but it looks like a very boring, blobby egg-shaped thing. Like I said, it's a very massive galaxy. These giant ellipticals are remarkable for their size and their stellar mass, like the number of stars they contain. On this scale, this is how big our Milky Way galaxy would be. So you can remember I said at the start, the Milky Way galaxy is a pretty big galaxy as these things go, 100,000 light years across. It's completely dwarfed by M87. M87 is this absolute giant of a galaxy that would dwarf anything inside of our local group. It gets even bigger as well. This is IC 1101, which is one of the biggest galaxies in the universe. It's the biggest galaxy we've ever found. Again, it's not that much to look at. It's an agglomeration of gravitationally bound stars without much kind of structure in it, so it looks a bit like a boring blob of light. But again, this is absolutely remarkable because of its sheer size. This is a cartoon of it. It's not quite accurate, unfortunately, but this is a cartoon that appeared in newspapers when we discovered IC 1101, giving the idea that it's around 6 million light years in diameter. You can see it is much, much larger than M87, and the Milky Way and Andromeda kind of vanish into nothingness when compared to IC 1101. 6 million light years across is a ridiculous size, right? It's big enough to swallow the Milky Way and Andromeda and all of the space in between. It's an absolute galactic giant. So these giant ellipticals are fascinating for astronomers for a couple of reasons. I mean, first of all, because of their sheer size, right? I mean, it was something of a challenge in galaxy evolution to understand how such a massive amount of stars could all come to be dwelling in the same place. They're also very interesting from a galaxy evolution point of view, because these massive elliptical galaxies are all dead galaxies. So just to explain what that means, normal galaxies like the Milky Way are constantly forming stars, right? So hiccups, excuse me. Normal galaxies like the Milky Way are constantly forming stars, right? So our Milky Way forms a handful of new stars per year. They take gas, which is the raw material for star formation, and process that into stars. That's the kind of like the heartbeat of galaxies' life, right? Taking gas and turning it into stars. Virtually every galaxy is doing this. Andromeda is making 1 or 2 new stars per year. The Milky Way is making kind of 3 or 4 new stars per year. The Magellanic Clouds are making new stars. It's a completely normal process for galaxies. But these massive elliptical galaxies are what we call red and dead. They're not doing this. They're not doing much at all, in fact. They're just sitting there being relatively boring. They're not making any new stars. So yeah, we say they're dead galaxies because they're not forming new stars, and we say they're red galaxies, and that's because they haven't formed any stars for so long. All of the stars have died out apart from the old red stars. Any kind of young hot blue stars would have died out billions of years ago, right? So as best as we can tell, these giant elliptical galaxies have not had any significant star formation activity for billions and billions of years. They're essentially relics of the early universe. And to be an astronomer coming across one of these red and dead galaxies is essentially like being a paleontologist coming across a dinosaur skeleton or something, right? If you're digging around in the desert and you find something like this, it would tell you that there is, or tell you that there would have had to have been some extraordinarily large creature living in the past, and you have just kind of come across its remains. For an astronomer coming across one of these massive elliptical galaxies, these are the dinosaur skeletons of the universe, right? It's telling you that there must have been some extraordinarily massive galaxy forming in the distant past that has left behind this kind of dead remains of a galaxy. So what we want to do is go and look back in time and find our dinosaurs and see if we can tell what kind of process has formed one of these enormous dead galaxies. I imagine you will all be familiar with the idea that astronomers have an advantage over archaeologists, that we can actually look back in time, right? The further away we look in the universe, the further we're looking back in time. So the sun is about 8 minutes away, and so we're seeing 8 minutes back in time when we see sunlight. And things in our Milky Way galaxy might be tens of thousands of light years away, so we're seeing tens of thousands of years back in time when we look around our galaxy. And then when we look around our local group, we're seeing millions of years back in time, right? So light from Andromeda has taken 2.5 million years to reach us. So we're seeing 2.5 million years back in time. The problem is that even millions of years is pretty small potatoes compared to the age of the universe. The universe is 13.7 billion years old, 13,000 million years old, right? And so going back merely millions of years isn't really going to cut it if we want to look into the deep past of the universe. So we want to look really, really, really far away and see if we can catch these behemoth galaxies in the act of forming. One of the best looks into the early universe we've ever got was taken by the Hubble Space Telescope. It's called the Hubble Deep Field. And it's very, very tiny patch of sky just off the end of Ursa Major. It's about a 1/12 the diameter of the full moon, or I tell children it's about a quarter the size of your pinky fingernail if you hold it at arm's length against the sky, just to give you an idea of what a minuscule patch of sky this is. So this frontier field taken with the Hubble Space Telescope was one of the pioneering science projects that the telescope did when it was first launched. It chose the patch of sky just off the end of Ursa Major because it was particularly empty, right? There's a very low dust obscuration from the foreground Milky Way, and so it provides a very nice, unimpeded, unobscured look back into the very early universe. And after about 3 weeks of integrating, so like a 3-week long exposure photo, Hubble took this photo. This is one of my favorite photos of all time. It's the Hubble Deep Field. Everything in this picture is a galaxy, and that's what's extraordinary. It looks like a starry night to start with, but then you have a bit of a perspective shift and realize that every single point of light, except for there's a couple here which are foreground stars in the Milky Way, but apart from these two bright things, everything in here is a galaxy. There's about 10,000 galaxies in this picture alone. And there's everything from nearby galaxies. You can see some of the larger spiral things are recognizably galaxies, so they are fairly nearby. But even this faint, almost noise you can see in the photo with these tiny little specks of on the very distance, these are galaxies that are right across the other side of the whole universe. Right, these are some of the earliest galaxies formed around 12 billion years ago. So this picture provides an excellent kind of vertical slice of the universe, if you like. You can see everything from fairly late time galaxies that are mature and fully formed, and then you can see in these very, very faint little dots, you can see these very tiny baby galaxies. I think this one here is a particularly ancient one, this red dot. You can see it's very bright red because the light has been very strongly redshift. So this is a real relic of the early universe down there. The problem is that when astronomers look at this picture and when we study these very early galaxies, there's nothing that is remotely big enough or powerful enough to leave behind one of these massive elliptical galaxies. So these elliptical galaxies are some of the biggest galaxies there are, right? They might contain 1 trillion stars. And to form that many stars in a relatively short space of time would be a cosmic fireworks show, right? It's a huge amount of energy in star formation. Any one of these things forming should just be absolutely lighting up the sky and shining out like a beacon from the early universe. But there's essentially nothing there. All of the early early universe galaxies we see in this picture and in other similar pictures are relatively puny and are the kind of things that would leave behind, like a Milky Way at best. So the question is, where are these things? I mean, these giant elliptical galaxies evidently exist. We can see them in the universe around us, but their progenitors seem to be missing in the early universe. So that is a bit of a puzzle. The answer to the puzzle relies on the wavelength of light that we're looking in. So the Hubble Deep Field is a optical, or essentially optical picture. I think there's some very, very near infrared and some near UV thrown in there as well. It's essentially optical light. So the question is, what about other wavelengths? Can we use other wavelengths of light to potentially find what might be hidden in this picture? The answer is yes, obviously, otherwise I wouldn't be telling you this. Long wavelength light in particular is very, very good for finding hidden things and revealing hidden information. If you look in the infrared, for example, you can see information that's not apparent there in the optical, like looking at two glasses and knowing that one of them contains hot water and one of them contains cold water. So the switching to long wavelength light is bringing you more information than is apparent in the visible. It's also very good for finding obscured things. This is a picture of some bushes. Switching to the same view in the infrared, you can see a person is standing in the bushes. This is why police teams, when they're searching for fugitives, go in with infrared goggles. They can see people hiding in the bushes, or firefighters, for example, going into burning buildings will use infrared goggles to penetrate the gas and the smoke and the dust and see the people kind of hiding inside. So as a general rule, long wavelength light is a very, very useful tool for seeing through obscuring material and revealing what is really there underneath. The long wavelengths I'm going to be talking about in this talk are what we call the submillimeter. So the submillimeter is technically the area of the electromagnetic spectrum of where the wavelength is around a millimeter or so. So this is the electromagnetic spectrum that we all know and love from school. You can see this is the visible part of the spectrum here, and then stepping to longer wavelengths, we have the infrared before we hit the microwaves and the radio. Submillimeter light is basically as far as the infrared goes. It's where the boundary of the infrared really rubs up against the microwave and the radio part of the spectrum. So it's basically maximally infrared light. Submillimeter light is very, very useful and very interesting for observing the universe, as I'm going to explain in a moment. What we use to observe submillimeter light is a kind of detector called a bolometer. So if you're observing in the optical, we tend to use CCDs, which are the same thing that powers your camera phone. We can't use a CCD in the long wavelength because the physics of the photons that are very low energy just don't work in the same way with CCD materials. So we have to use something called a bolometer. Bolometers have a long and storied history. The word bolometer means measurer of known things, which is one of the most useless etymologies I've ever come across. They were invented by an astronomer in the 1870s, a guy called Samuel Pierpont Langley. Came up with the first design for a bolometer, this device for sensing very, very long wavelength radiation. It's based on the idea that resistance in a circuit is a function of temperature, right? So you build a little circuit in your instrument, and then if you have long wavelength radiation, which is essentially heat radiation, right, coming through, it will warm up your circuit, and you get a little resistance spike, and then that will tell you that you've detected some very, very long wavelength photons. The first outing of a bolometer was very auspicious. Samuel Langley was able to detect a cow just purely from thermal radiation at a distance of about 1/4 of a mile, which kind of sounds faintly ridiculous, but is actually remarkably impressive if you think about it. Essentially a remote thermometer from 400 meters away, he was able to detect the heat radiating off a living creature. So this is a bolometer, essentially a heat sensing device, a kind of directional thermometer for sensing very long wavelength radiation. The reason they weren't used for astronomy for a very long time was because until the 1990s, bolometers were all single pixel devices, right? They were invented way back in 1878, but there's a reason we didn't start pointing them at the sky straight away. And that's because they were all single pixel things, and mapping the sky with a single pixel instrument is essentially impossible, right? Imagine how much of a nightmare it would be to have to use your camera phone with 1 pixel and build up a picture of something. The breakthrough came when we learned how to multiplex bolometers together with superconductors and stick several bolometers together, each acting like individual pixels to make a bolometer array that could act essentially like a crude camera. The first widely successful example was called SCUBA, SCUBA meaning the Submillimetre Common User Bolometer Array, which was mounted here on the James Clerk Maxwell Telescope on the summit of Mauna Kea in Hawaii. SCUBA completely transformed astronomy. It was the first look in this whole new wavelength regime into space. You know, there have been several revolutions in astronomy where we've managed to get an entirely new wavelength look into the sky, right? We've been doing visual astronomy for thousands of years. People like Gruit-Reber and Jansky invented radio astronomy in the 30s and 40s, and that was an entirely new way of looking at the universe. When we developed infrared astronomy and went to space in the 1970s, again, that was an entirely new way of looking at the universe. And this is another one, I think. The SCUBA and the ability to study the sky in these submillimeter wavelengths was a revolution in astronomy. This is SCUBA itself. It's still a far cry from the millions of pixels that we have in our phone cameras. There are 37 bolometers multiplexed together inside SCUBA. You can see it looks like this little honeycomb thing. Each one of these tubes is an individual bolometer. So 37, you know, again, it's not quite the kind of 10 megapixel camera you might wish for, but still 37 is a lot more than one. And so with this, you can actually start to take pictures of the sky. I will say, normally I would do a show of hands if we were doing this in person. I'll just have to pretend. I'm always keen to know who has heard of SCUBA, because it's not very well known outside kind of enthusiast circles. People are often surprised when I tell them that in terms of citation rates, if you kind of count all the papers that have come as a result of a particular instrument and count their citations, SCUBA is the second most successful astronomical instrument of all time, second only to the Hubble Space Telescope. So, you know, think of the amount of press that Hubble gets, and SCUBA, this one little 37 pixel long wavelength camera, is second to the Hubble Space Telescope in terms of the impact it's had on astronomy. It's a very, very important instrument. And that's what I just said, 37 Volometers all linked together to actually image in millimeter wavelengths. So when we built SCUBA in the late 1990s, the first thing we wanted to do was to image the sky and kind of replicate known things, particularly this Hubble deep field. One of the first projects that went ahead with SCUBA was to do a SCUBA deep field, to take this same patch of sky that had been observed by Hubble and observe it with SCUBA, observe it in these long wavelengths, to see what we could see. I'm going to show you now the results of SCUBA versus Hubble. So believe it or not, this is the same patch of sky. So on the left, we have the Hubble deep field as seen by Hubble. And then on the right, we have a mirrored identical, we have a mirrored identical patch of sky as it is seen by SCUBA. So it looks, first of all, it looks very different. It looks a lot less pretty. It looks like a kind of ugly blobby mess. When you look at these pictures, it becomes maybe a bit obvious why SCUBA doesn't have the press attention that Hubble has. It tends to observe blobby things rather than kind of nice, very sharply defined pictures. The blobbiness is simply a function of the resolution of the camera. The wavelengths that SCUBA is observing are 1 million times longer than optical wavelengths. And so, the resolution of your images is necessarily going to be like 1 million times worse, basically. So that being that, once you've got over your shock about how kind of blobby and ugly the picture looks, you can start noticing some very, very interesting things here. In particular, what's really notable is that the bright things in SCUBA do not correlate with the bright things in Hubble at all. Take this one. This is known as HDF1, the brightest thing in the SCUBA deep field. If you look in the Hubble deep field where HDF1 is, there's essentially nothing there. This is a zoom in of the patch of sky where the brightest SCUBA source is. And this is where the SCUBA source is, and there's nothing particularly notable there in Hubble. It would be one thing if the very bright SCUBA things lined up with the very bright Hubble things, and that would make sense because the bright galaxies are just dumping energy out at all wavelengths. But it seems to be that there's something in this patch of sky that is generating vast amounts of very, very long wavelength radiation, but is completely missing in the optical image. So what are these things? This is the first question to ask. So they are galaxies. They are emitting lots of long wavelength light, but they're not showing up in optical images. One of the first questions you can ask is how far away are these things? Are they, relatively local universe phenomenon? Are they a bit more distant? I want to do a bit of a sidetrack at this point, because there is something very interesting about this submillimeter, which lets you observe very, very, very distant things in a way that's much easier than it is at shorter wavelengths. This gets called submillimetre magic. Astronomers and scientists don't use the word magic lightly. This really is a very, very nice effect. So the effect is this: galaxies observed in the submillimeter don't obey the normal distance brightness relationship. So a normal galaxy or a normal object follows what we call the inverse square law. So as the galaxy gets more and more and more distant through space, the brightness of this galaxy will drop according to the square of the distance, right? So you put a galaxy twice as far away, it will get 4 times fainter. Put a galaxy 10 times farther away, it will get 100 times fainter. Galaxies observed in the submillimeter don't do this. They stay exactly the same brightness across a huge range of distance, which means that the submillimeter is an amazing way to probe the very, very distant universe, right? In the optical, things that are nearby are bright and things that are far away are very, very faint indeed. In the submillimeter, things that are nearby are bright and things that are very, very far away are bright as well. I want to explain how this actually works, because this, at first glance, this is fairly baffling. It seems like these submillimeter galaxies are defying the fundamental laws of physics, right? This seems almost impossible. So I just want to take a moment to explain how this works. It's quite neat. To explain how this works, I want to introduce this idea of a spectrum, which I imagine lots of people here will be familiar with. The idea is essentially a graph of brightness against wavelength, right? So you have brightness on this up and down y-axis, and then wavelength on this bottom x-axis down here. And you'll notice the wavelength here is fairly short. This is just an optical spectrum of a galaxy. We can step back a bit and look at we can step back a bit and graph the brightness of a galaxy across the entire electromagnetic spectrum. This is something called a spectral energy distribution. So it's the idea of a spectrum, but just stepping back and just looking at the galaxy across the entire EM spectrum and seeing how bright it is across this massive range of wavelengths. So this is a real galaxy. This is ARP 220, I think, one of the very kind of bright, unusual galaxies in the local universe. It's brightness on this y-axis and then wavelength on this x-axis down here. The x-axis is logarithmic, so you have this enormous range in wavelength, like a factor of 10 million between the left and the right. And we can actually just try to chop this up into the more familiar parts. So this left bit down here is showing you the UV and optical. So the galaxy is pretty faint in the far UV and gets brighter and brighter and brighter until it's reasonably bright in the optical. It's about the same brightness in the near infrared as it is in the optical, and this far infrared, it gets very, very bright, right? So this big kind of hump here, this is the signature of cold dust in this galaxy, this very, very bright hump. So this galaxy is hugely bright in the far infrareds. Then this is the submillimeter down here, this slope downwards, and then this long wavelength tail is the radio. So you can see there's a lot going on here, and the shape of a galaxy's spectral energy distribution will tell you a lot about what is going on with that galaxy. So what I want to do now is to simulate the effect of moving this galaxy further and further back through the universe, and so we can see what happens to the brightness at different wavelengths. So there's two effects when you move an object further and further away through the universe. First of all, it's going to get dimmer. Obviously, that's basic physics. You can't get around the fact that if something gets further away, it gets dimmer. So the first effect is that as the galaxy gets more and more distant, it's going to get dimmer and dimmer and dimmer. The second effect is, of course, redshift, right? We live in an expanding universe. And so when you move a galaxy further and further away, it's going to pick up more and more and more speed due to the expansion of the universe. And so it's going to get more and more and more redshifted. That's why very distant objects in the universe have these very, very large redshifts. And what a redshift means, it's a shift towards longer wavelengths, right? So the spectrum is going to shift to the right. So these are the two effects that we're playing with. When you move this galaxy further out into the universe, it's going to get dimmer, go downwards in this plot, and it's going to get redshifted, move right in this plot. Okay, so you can actually do this. And so this is, I've taken this galaxy and I'm going to move it further and further and further and further away. So the black one is fairly nearby. The blue and the kind of turquoise and the green, they get progressively further away until we reach this red one, which is very, very far away indeed. And so we can imagine that we're observing these, so imagine that we have 6 different galaxies, right, nearest to farthest away, and we're observing them. If we observe them in the optical, so remember this bit down here, you can see it behaves fairly sensibly. You get the nearest one is brightest, and then they get fainter and fainter and fainter and fainter as they get further away. If you observe them in the radio, you see the same thing. The nearest one is very bright, and they get fainter and fainter and fainter and fainter and fainter as they get further away. Everything's behaving very sensibly. In the submillimeter, though, something very interesting happens. To start with, you do get a bit of a drop, right? So the nearest one, and as you move it away, it drops a little bit. Then after a little while, with distance, the galaxy doesn't get any fainter. All these lines start overlapping. And that's because these two different effects, the dimming effect and the redshift effect, are actually cancelling out, because as a galaxy gets redshifted more and more and more, the brightest bit of the galaxy's spectrum is getting redshifted into your observing band. Remember this very, very bright hump in the far infrared, that's all the cold dust in this galaxy. As a galaxy gets redshifted, you're observing an intrinsically brighter part of the galaxy spectrum, and that completely undoes the effect of dimming, right? So you move a galaxy twice as far away, it gets 4 times dimmer, but then you're observing a part of the spectrum that is intrinsically 4 times brighter, and the galaxy you see stays exactly the same brightness. it's this amazing thing. These two effects just march completely in lockstep in opposite directions. So across this vast range of distances, galaxies are exactly the same brightness. This is a normal galaxy. This is a kind of brightness versus distance cartoon. In a normal galaxy, it will do something like this. Observed in the submillimeter, galaxies do something like this. So across this enormous range in distance, galaxies observed in this particular submillimeter band, where the wavelengths of light are around a millimeter, galaxies stay exactly the same brightness. And that makes the submillimeter the best possible tool for studying the early universe. If you are an optical astronomer or a radio astronomer and you want to study very, very, very distant objects, you are struggling to find individual photons. When you hear these results, when people find the most distant ever galaxy in the optical, and it's something at redshift, redshift 10 or something, when the universe was 500 million years old or so, those observations are made based on one or two or a handful of photons. Observed in the submillimeter, though, things just stay exactly the same brightness. We can study the early universe just as easily as we can study the relatively nearby universe. With a sufficiently sensitive submillimeter observation, you can essentially see everything that there is to see back to the very start of the universe. The submillimeter is the most amazing tool for understanding the early universe. Of course, there's a downside. Brightness being independent of distance means that there's no actual way to tell what the distance is, right? If you're observing in the optical and you see something very faint, then it stands to reason that's far away. In the submillimeter, a bright blob could be relatively nearby, or it could be very, very distant across the other side of the universe. This took a bit of cleverness to get around, which I can talk about in the questions if you like, but I think it's a bit of a sidetrack. Basically, we had to work out a way of locating the actual position of these things inside the fuzzy blob, so we could take a spectrum of them and really pinpoint their redshifts. But my main point is that observing at these submillimeter wavelengths is a fantastic way to find these very, very distant galaxies. And when we observe, when we actually measure the redshifts of these new galaxies, remember the whole point was that we turned SCUBA on, this new submillimeter observation facility, and we found all these submillimeter bright blobs that didn't correlate to anything that we saw in the optical. They are very, very, very distant indeed. They are all, they live between, in astronomer language, they live between redshift 2 and redshift 6, which is essentially anything from 8 to 12 billion years in the past. Just to kind of put that in context, if we draw out a timeline of the universe being about 14 billion years old, the Earth formed about 5 billion years ago. This is where our hidden galaxies live. They really, really are some of the first big galaxies ever formed. They live at these extraordinarily high redshifts. We're looking at, they live, when the universe was about 5% of its current age. So I'm assuming you have all guessed the punchline at this point, right? But of course, we've found this new population of galaxies that were completely hidden before, right? These galaxies were completely invisible before we turned this new submillimeter telescope on and discovered them. They are very, very distant. They are very energetic. They're pumping out huge amounts of energy in the submillimeter, and they only live in the early universe. They are the perfect match to explain these massive red dead ellipticals that we see in today's universe. So essentially, we've found our dinosaurs, right? We've found our kind of cosmic ancestors of these massive ellipticals. So we call these galaxies submillimeter galaxies. I wish this was a photo of a submillimeter galaxy. Obviously, it's not. It's an artist's impression. The word it feels a bit strange calling them submillimeter galaxies because that kind of calls to mind something that's pretty tiny. These submillimeter galaxies are anything but tiny. They are the biggest and the baddest and the most extreme galaxies in the universe. What makes them so extreme is really the rate that they're forming stars. Remember that these submillimeter galaxies are the ancestors of massive ellipticals, right? So these are essentially, they have to result in 1 trillion stars or something being formed. A submillimeter galaxy is essentially the biggest star formation cosmic fireworks show in the universe. They can easily have star formation rates of thousands of stars per year, which just absolutely dwarfs anything that we would see in the universe around us. Just to put this in some kind of context, the Milky Way forms a handful of stars per year. A galaxy that we think of as a local starburst galaxy, something like M82 or ARP220 or something, might form 50 or 100 stars per year. A submillimeter galaxy can easily form thousands of stars per year. They, in terms of their efficiency of their star formation and just the number of stars they're churning out, they completely dwarf anything in the local nearby universe. They are the biggest and the most efficient factories for stars in the entire universe. How are we doing for time? Okay, let's get one more thing. So these things are interesting for a couple of reasons. I mean, firstly, they're interesting because they are the biggest, the most extreme star formation environments in the universe, which is fascinating in itself. They're also really fascinating for astronomers because they really throw a spanner in the works for galaxy evolution theories. The real issue that we're trying to solve is, how do you get a galaxy to form stars that fast? It's quite difficult in terms of our theoretical understanding to work out how you can get a galaxy to form thousands of stars per year, year after year after year. To give you a flavor of the argument, I've got, obviously, stars are made from gas, right? So this very, very high star formation rate must mean that there is a huge amount of gas living in these galaxies to fuel this massive starburst. And so one of the questions is, where does this gas come from? How do we fuel this starburst? Two main ideas are, maybe you could crash two galaxies together. Even in the local universe, when you merge two galaxies together, that triggers a huge starburst. And so maybe if you take two very, very massive, very gas-rich galaxies in the early universe and crash them together, that could maybe fuel some kind of enormous starburst that we're seeing. Alternatively, maybe rather than crashing two galaxies together, maybe you could just have a single galaxy, but you could just throw gas at it. The galaxy might sit at the intersection of some cosmic filaments that are like giant kind of cosmic waterfalls of gas that just pour gas down onto the galaxy because of the galaxy's kind of gravitational potential. These are two different ideas for how one of these galaxies might actually function. Neither of them really work, though. There's a serious problem with both of these things. First of all, this idea of crashing two galaxies together, this kind of works in theory. This is an image taken from a supercomputer simulation of two of these submillimeter galaxies. So it's perfectly possible to build a little box of a universe inside a computer and take two massive gas-rich galaxies and crash them together and generate something that looks like a submillimeter galaxy. It works in theory. The problem is, from cosmological simulations, and this video never works, I'm really sorry. I forget the video. So we have these cosmological simulations, like the Millennium Simulation or Illustris, that some of you might be familiar with. When we look at these simulations, they give us a very, very good idea of how structures form in the early universe and how common it is for galaxies to crash together. And everything we learn from simulations that are tuned very carefully to replicate the universe as we know it, these simulations tell us that merging galaxies should be reasonably rare, at least these very kind of massive major mergers. But submillimeter galaxies are everywhere, right? They are a lot more common than the simulations say they should be. So saying that these submillimeter galaxies are all these two massive galaxies crashing together doesn't really work, because it contradicts something that we know from simulations, which is that mergers are reasonably rare. An alternative idea is that you can drop the whole merger thing and say that these submillimeter galaxies are powered by inflows, right? Again, this is a computer simulation of what one of these might look like. You have a relatively normal galaxy, and then you have these cosmic filaments where cold, pristine gas kind of rains down onto the galaxy and fuels this kind of extreme starburst. An issue with this, of course, is that stars push back a little bit. So anyone that's seen the Northern Lights will be familiar with the idea of the solar wind, right? There's a wind that blows from the sun and strikes the Earth's magnetosphere, and we see that as the aurora borealis, forming thousands and thousands of new stars every single year. The combined force of those winds, and young stars when they're just formed have particularly strong winds, the combined force of thousands of new stars per year being formed should be enough to blow all of the gas out of the galaxy. it's like a negative feedback thing. There's an intrinsic pressure valve to this kind of star formation where you're just throwing gas at a galaxy, which is if you start forming stars too fast, the galaxy just blows all the gas away and then the star formation is going to drop. So again, this doesn't seem like it's the solution. It's quite hard to solve this problem. Most of the theoretical ideas for how SMGs, submillimeter galaxies, really work don't do a good job of explaining the observations that we see. One real problem is caused by how hard it is to see these things. At the current time, our best image of an actual submillimeter galaxy looks something like this. That's because even though these things are bright, because of this submillimeter magic that keeps things very, very bright all the way through the early universe, they're still far away. And so they're still small when we're observing them with a wavelength 1,000,000 times longer than optical light. And so that makes the resolution a very, very hard thing to chase. So this is a submillimeter galaxy living in the early universe. It's very hard to see what's going on here, right? Compared to optical studies where we get these very, very nice pictures where we can fully kind of dissect and diagnose what's going on inside a galaxy. So what we might have to wait until the next generation of instrumentation. It's going to be a while till we get anything that looks as nice as this, but luckily we do have 2 instruments on the very near horizon that are designed for long wavelength study. The James Webb Space Telescope is the successor to Hubble, is fingers crossed, launching next year, and that's going to carry with it a suite of infrared instruments that are going to be able to study galaxy formation in the early universe better than ever before. And also the Square Kilometre Array, which is going to be coming online gradually over the next decade, which is a radio facility with a sensitivity and a resolving power that almost seems like science fiction. It's going to be an absolutely enormous leap forward in terms of radio studies of the universe. So, and as of right now, submillimeter galaxies are a bit of an enigma. They are some of the most extreme, to me, the most interesting galaxies in the universe. And it's not quite clear how they function or how they fit into our models of galaxy evolution. So I'm looking forward with great anticipation to the next generation of instrumentation that will hopefully find us some answers. And that is where I'm going to stop.